dating. All right. Glad to see that you survived the minus 40 below. All right. Of course, when we have an event like that, it always comes with some sort of flooding. Okay, especially related with civil engineers at Notre Dame. I don't know about that. Okay. It's the second one I experienced in 2.5 years. And there may be a third one because it's going to start raining. And you know what's going to happen to all that snow. So I worry on that. Okay? All right. So what I was planning to do actually initially, like as of 10 minutes ago, was to first go back and review some of the things we discussed past on the earlier lecture, and then do some new topics to finish this lectures on decision theory. So what I'm going to do is I'm going to do the opposite. I'm going to cover first the things that are left in the notes, and if I have time, I'm going to come back and emphasize some of the things that we missed on the lecture a few days ago. So this part is sort of, if you have seen it before, there's nothing difficult, and the concepts are sort of generic. They're applied not only in the context of classification and decision making, but to many different types of scenarios in machine learning. So let me introduce some terminology that may be familiar to you. So think we classified something belongs to class 0 or 1. So we don't really know the truth. We don't know if, so the truth here is denoted with y. So we don't know if y equals to 0 or y equals to 1. And so what y hat is our estimate, is the result of our classifier trained with some data. So the terminology here is a false positive is when we declare something to be class 1 when the true class is 0. So think of 1 being positive, 0 being negative. So we estimate to be positive when it is negative, and false negative is we estimate to be negative when it is positive. We need to introduce some loss function to be able to do calculations for this type of things. And there is no loss if we do the correct guess. So if we guess y equals 1 when the true label is y equals 1, the loss is 0. Similarly here. So this is the false negative and the false positive loss functions. All right, so what usually you do is, especially in the context of binary classifiers, you have to come up with a matrix that you account for all of these things, that labels that you see up here, and all of this, so true positive, false negative, true negative, and these sums of the different configurations that you come up with. So what you see on the horizontal row is the truth, so that's y, and on the vertical thing is what the estimator gives you. So for example, true positive is your estimator gives you that it's true when actually it is true, or here the estimator tells you that it's true when actually the truth is that it's negative, it is 0. So n plus is the true number of positives, n minus, if you sum this column, is the true number of negatives, and n plus with a hat is how many times you call this to be positive, okay? So it's the sum of this row, and this is the sum of that row. So this matrix is called the confusion matrix, okay? And sort of, you know, you're going to have once you train the classifier, you will actually have to come up and fill it up with all of this information. So in many papers, even published today, right? So if you are going to evaluate your classifier versus models available in the literature, you're going to have to do this sort of the analysis that you see here. So the only thing I want on this slide to emphasize is that somehow when we make a decision in the estimator, if something is has labeled 1 or 0, we're making those decisions with some threshold. And if you remember from the earlier lecture, we based all the decisions on this posterior distribution of p of y equal to 1 given x. So you can think a classifier that says when this probability is above one threshold, we assign the label to be 1. And that threshold is to be computed. It depends basically on a lot of different things. And so we need to explore how we actually evaluate the performance of the classifier for different thresholds tau. So I emphasize this is going to come in the next picture and the next slide you're going to see. When you compute this and you're going to say, oh, I am class 1 or it is positive, you can only say that with some tolerance. And so we would like to actually build a classifier that gives us results for all possible tolerances. Okay? So we would like to do this not just for one tolerance, but for all possible tolerances. Okay, so let me define the quantities here. It will take you some time to get used to the terminology, but I think if you use sort of the down-to-earth meaning of these acronyms, you will guess correctly. So I'm going to define what's called a true positive rate, all right? And that is basically the ratio of the true positive divided by n plus, where n plus is the number of true positives. Remember, this is, you know, the truth column, so TP plus Fn, which is n plus, is the true positives. So TP is how many times you declare something to be positive when the truth was positive. All right? So how many times you declare your classifier gave you that something is positive when the truth was positive. So that's the true positive rate. And similarly, I define what's called the false positive rate, all right, which is Fp divided by n minus 1. So from all those that they were truly negative, how many times did you wrongly declare them to be positive? Okay? So true positive rate versus false positive rate, okay? Tp over n plus and Fp over n minus, and there are many other things that you will see later in the slides. So what I want to do is, I want to plot the true positive rate versus the false positive rate as a result of the classifier, but for all possible values of the tolerances T that I use in my classification process. Not just for one tolerance, but for all possible values of tolerances. And I remind you, more or less everything is based, let's say if you have a binary classifier on this posterior probability, so we're going to have to put some threshold that above some value, we will declare this to be positive, below to be negative. So that is the threshold tau. So what I want to do is I want to plot this versus that for all possible values of tau. And the curve that you get is called the receiver operating characteristic curve. And you see two of those. This is one example with this blue curve. This is the other example with the red curve. You obtain this by plotting the true positive rate versus the false positive rate for all possible values of the tolerance tau of the classifier. Okay? So there is, I make up an example that you will see in the slides coming up, but effectively each value here, it's a different value for tau. And what is the optimal curve that you can achieve in a classifier? I mean, ideally, how would this curve look in the most ideal case? What is the number of the true positives that you would like to see in your classifier? What is the number of true positive rate that you would like to see? So give me an exact number. 1, right? And the false positive rate would be 0. So really, ideally, what you would like is this curve to be touching this vertical line, and then be asymptotically parallel to the line 1, okay? So that's the ideal situation. And again, here I remind you that this is the decision making. So if the posterior is higher than some tolerance, then the label that I assign is 1, otherwise I assign 0, okay? So the ideal thing is touching the vertical, the horizontal line. And another way to represent this curve is what is called the area under the curve, which you see here under the blue curve. So this you can consider as sort of being an average true positive rate, okay, over all the ranges of the false positive rates. All right, So here's an example. Okay. So imagine that you collect different data. Okay. And these are the true labels. All right. So this is your training data set. So we're assuming this is supervised learning. So I have a horizontal line here to separate the true positives from the true negatives. And these are, the classifier basically gives you these probabilities. Okay? So what you do is, you're going to be setting to design this curve, to plot it, you're going to have to evaluate the classifier for different tolerances. So I have here the column for tolerance equal to 0, tolerance equal to 1, and let's say somewhere in between tolerance equal to 0.5. So if the tolerance equal to 0, how many times do you accept your data to be positive? Remember, the decision again is, if this is greater than tau, then it's positive. So how many, if tau equal to 0, how many of your samples are positive? All of them. If the tau equal to 1, none of them. Okay? So let's take somewhere in between, and I make up some numbers. So pick up one of those. Let's pick up this false positive rate is the false positive divided by the true negatives. How many true negatives do I have in my problem? What is n minus? True negatives. You remember these are the true labels, right? This is a training data set. So how many true negatives I have? 4. And how many times from the true negatives I declare something to be positive? 1, because it comes with probability 0.6, right? And my tolerance is 0.5. So, so you calculate for tolerance 0.5, the false positive rate to be 0.25. Similarly, the true positive rate to be 0.8, and there is 1 point. And you continue doing this for many points, okay? And somewhere actually, if you search on the web, there is a script written, I believe, in Python that sort of you provide your classifier results, or you provide basically the classifier results for a given tolerance, and it plots, it calls the classifier, it compares with the true labels, and it plots this thing for you automatically. Okay, so this is an expensive calculation to do, but effectively you cannot go arbitrarily and set this tolerance. You have to do this type of analysis. All right, so let me discuss why this. So what we plotted here, right, is true positives versus false positives, and you notice the false positive rate is the false positives divided by the number of true negatives. So let me pose the following classification problem. You are given an image, a big image, and you want to find in little windows that you are going to split this image, how many times you meet a car. So can you tell me how much is n minus in this context? N minus means no car. Well, I mean, I only give you 3 windows, but how many windows can you take there that there are no cars? How many? As many as you want, really. Okay? So basically, what you saw before, when you try to, to apply it to some recognition problem in images, for example, this talking about n negative here, all right, n minus, is not going to work. It's not going to work because literally this number of windows where you don't have a car, not only it's undefined, it's really part of the algorithm. It's not part of your training data. I mean, you can say in the algorithm, use windows of this size, that will give you maybe 1 million windows versus windows of that size that will give you hundreds of windows. So what you need to do is, in that case, you need to change the type of curve that you plot for different precisions, and that leads to what is called a precision recall curve, where you plot the true positive rate versus the precision, and here is the definition. And the only thing I want you to pay close attention is, in this type of recognition problems, you only talk about positives, okay? Because talking about negatives it's not appropriate. So in this case, we say from the true positives, how many times the classifier declares something to be positive. And the other way around, from the ones that you declare to be positive, how many were actually positive? Okay? And considering that so here I change the notation a little bit. Okay, no, actually, no, the notation is the same because all the labels are y equal to 1. So effectively, you can write this, all right? You can write it like that, okay? And this curve is called a precision recall curve. And the optimal situation now, it is when this curve is actually asymptotically touching the true positive rate to be equal to 1. So coming this way, touching down all the way. Okay, we discussed this. I gave you the definitions. And lots of times, and you can, there's a separate Wikipedia site on this. If you want to declare only one, rather than having the whole curve to describe things for different tolerances, you may want to provide one score for your classifier, and the score that usually is advocated here is what is called the F score, and it is really nothing else but the geometric mean of the precision and recall. So 2 pi r divided by r plus p, and if you do the substitution, you get something that looks like that. So this is the F score. Now, in reality, you can find a lot of counterexamples that realize that this is very murky territory because this F score may be completely useless. And so here is an example. So imagine that you have 3 classifiers, A, B, and C, that try sort of to classify the same thing, right? But you build them in a different way. So what you see here are the true labels, okay? And this is what the classifier gives you. These are counts, all right? And looking at this, right, can you tell me which classifier to you looks questionable? Or, which classifier is not going to make you very happy? I mean, if I look at classifier A, does it declare anything to be negative? It puts most of the probability, as you notice here, of something being declared positive if it is positive, okay? And so there is nothing to be negative here, so this is not very good, okay? Cannot be the case. Now, and if you compare B and C, all right, they look similar. The only difference is that the misclassifications, they are more for C than they are for B, because you can see here 0.12 of things that even though they are positive, they are declared negative, and here it's 0.1. So in some sense, B, you anticipate it to be better than C. So if you go and you compute the precision, you compute the recall, and you compute the F scores using the formulas that you have seen before, you realize that the formulas for F score, this geometric mean, is really not relevant to this problem. It's completely garbage, because it tells you that the classifier A is way better than the classifier B, which is better than the classifier C, okay? This is not the case. A is the worst of the 2 classifiers, C is the second worst, and B is the best. So how do you get this better? Mutual information, again, between the true and the predicted labels comes in the pictures. So when you compute the mutual informations between Y and Y hat, indeed, the arrangements, you can plug in here, perform the summations, and the evaluation comes that the mutual information for A is 0, for B is 0.18, and for C is 0.117. So B is indeed the best, C is the second best, and A is the worst. All right. If you try to extend these things to multiple classes, things sort of you need to rely on what we discussed for 2 classes. So there is 2 ways to do this. One is to average the F1 scores for each class individually, so you can classify one class versus all the other classes, right? So in this case, if you have class 1, class 2, class 3, you basically have to sum over the three classes. You classify if something is in class 1 or it's not in 1. If something is in class 2 or if it's not in class 2. So this is called a micro-average F1 score. And the other one, micro-average, is to actually pull all the resources together and come up with one contingency table and compute the F1 score from that table that involves all the score, all the numbers basically summed together. So if you look at these things on the bottom, let me just read it here and you tell me from where this comes. It says the precision of class 1 is 0.5. Where do I get that? Look at the numbers and tell me, in class 1, why is the precision 0.5? The definition of the precision, again, is the true positives divided by the numbers that your classifier declared positive. So how many samples in class 1 the classifier declared positives? How many? This is what the classifier does. 20. How many true positives do you have out of the 20? 10. So basically, the precision for classifier 1 is 0.5. Similarly, for class 2 is 90 divided by 100 is 0.9. So the macro average precision is basically 0.5 and 0.9 over 2, it's 0.7. Notice here that in class 2 you have a lot of data. In class 1 you have less data. And I'm actually curious if I typed this correctly. But anyways, here you can notice when we talk about true positives, you have 100 data versus 20. Okay? So in some ways, class 2 is overwhelming in this process. So let's calculate now the micro average F1. So what we will need to do is pull all the numbers together. So we had 10 here and 90 there, so we have 100, 10 and 10, 20. So the number now of these true positives, all right, divided by how many times you declare positive will be 100 over 120, so it's 0.83, okay? So the only advice that's given here is basically macro averaging is the best way to do things if you don't have the same sort of number of samples in all the classes, okay? But this is sort of what you have to provide when you have a classifier when you try to compare multiple classifiers with each other. All right, I can bypass this, and let me just discuss about this topic a little bit of. I don't know if we're going to have time to discuss about design of experiments later in this course, but if anybody's interested to do a project on this, there are courses completely devoted to this topic because it is sort of extremely important in the context of research and has applications on multiple areas, okay, from advertising things on the web and try to attract users to, as I said, design of experiments. So the usually the word bandit here, it is it's a buzzword for these machines that you have in casinos, right? So if you go to Macau, they have lots of these machines, okay? So effectively, we have a machine, and conceptually here, and they want you basically, they want to sell you, let's say, advertisements. So they try to sort of figure out what type of advertisements you're going to read, all right? And it's like you go to the web and you click different things, and they want you basically to go and click things that it would be beneficial to them for you to read. Because if you read them, then you will say, oh, I'm going to go and buy this car, okay? So what we have here is, we have data that involve actions, which actions here is what machine you're going to pull down, what bandit you're going to pull down. X is the futures of both the machine and yourself. So this is, for example, all the information Google and Facebook collect on you, all right? And R is the reward For example, if it's a binary sort of classification problem, R equal to 1 would be when you click and read an add, and R equal to 0 if you don't do that. Okay? So we have basically, they collect all this data, historical data on what machines you pull, what your futures are, what the rewards are, and these rewards are modeled through a regression model, okay? Depending if the reward, if R is a binary variable, you're going to use ideas of logistic regression, which we're going to do later, maybe in about a week or so in the course. If the reward is a continuous, you can use linear regression, which we will cover on Tuesday. But somehow, you're going to have some sort of a regression model that relates the future sex with the rewards. And here is the problem. The problem is to select basically the machine to pull down that maximizes the reward, okay? But it's not really just simply that to identify what machine will give you the highest reward, right? This is here the expected mean, the posterior mean of the reward, okay? So you want to pick up the machine K that will maximize that. But notice here, there's something else there. It says you can do this, and or you can pick up actually the machine that comes with the highest variance in the reward, something you have never explored before. So really, this type of optimization problems are exploring things. They are basically optimization algorithms that address this trade-off between exploration and exploitation. All right, you want something that maximizes basically your profit, but also you want to explore something that you have not seen before, so something that has higher variance. So this type of optimization problems, they are not trivial, and lots of them, obviously, they are posed in a game theoretic manner, and that's why these sort of ideas are very relevant to research these days. So the way you solve them is basically by computing posterior probabilities. So what you do is you say, look, there is the parameters of every machine, right? I have computed a posterior. The reward, okay? I can compute a posterior reward for given action that I take, for given futures and given parameters. So what you can do is find the machine, find the action that you need to take that maximizes the reward, and then for that reward, take the posterior with respect to the parameters of the machine. Okay? So you have to calculate this whole integral that you see here. That actually, just before I came, when I was looking, I'm not quite sure if the notation is correct here. So I want to describe what I want to tell you is, so obviously you can take many actions, right? You have the choice what to click on the web. You want to find the action that maximizes the expected reward, and then I wanted to put outside this indicator function, and then for that expected reward, compute its posterior mean. You see why the notation here is not good, right? The way the indicator thing will give me 1 or 0, but I want also to get out of this the actual maximal reward, okay? So I'm not quite sure how we're going to denote this. So find basically the action that maximizes the expected reward, right? And then compute the posterior of that with respect to the parameters of this Bandits. And an approximation of this you have to calculate it sort of with Monte Carlo. If you don't want to sample from this high dimensional distribution and average to do this with Monte Carlo, they suggest basically you can take even one sample and you calculate the posterior mean of the rewards and maximize this for different action scale. So you can place the optimization problem as simply as that. All right, so you know what? I covered some of the new things that I wanted to tell you. So now what we want to do is, with our luxury, we can go back and review and maybe give you some more hints on some of the things we have seen on this decision making. So I remind you that there is a true state that nature hides from us. We call it Y. We take an action A. We compute a loss function. I mean, we postulate a loss function. And then we compute the action that minimizes the expected loss. And we declare the expected loss that makes sense here is the posterior expected loss. Okay? So we don't really know why, but we have some observation X, and we want to figure out what the expected loss is with respect to that posterior, and then we need to find the action that minimizes that expected loss. All right, so all these Bayes estimators that we discussed are basically of that sort of nature. And I gave you a few examples, and most probably you read those in the notes. So here is, I'm giving you an X, right? And you're trying to guess if Y comes from this set Y0. Okay? So you're going to make sort of a guess, right? So you say alpha equal to 1, all right? That's your decision, which implies that Y comes from Y0. So let's see, if you declare that it comes from Y0, alpha equal to 1, so if indeed Y comes from Y0, then the loss is equal to 0. You see that? But if you say it comes from Y0, but actually it is not, then your loss is equal to 1. And the other way around, when you declare that Y is not coming from Y0. Remember, this is a guess. This is the truth that you don't know. So what you need to do is you need to take a posterior expectation of this, and then it comes, you get the posterior expectation looks like that. And to be able to actually select what your Bayes estimator is going to look like, you have to decide, so you know, if you're, let's say for alpha equal to 0, you're going to select this, the implication is what? That this loss has to be less than that loss. So when you do the calculations, you get the obvious result that you will select that X indeed belong, you know, that Y will be basically in that class, that's your guess, if the posterior probability is less than 50%. Okay? So what we usually apply in practice using common sense, right, it does come actually from the postulation that there is a loss function that we try to maximize under some posterior distribution. So it's really, there is a lot of mathematics basically why this is, leads to the obvious, obvious answer. We talked about the L2 loss, all right? That's the most common loss, and the decision basically, the estimator, it is the posterior mean of Y, all right? So that you see here, okay? So when you see posterior mean is, it's always based on the L2 loss. I modify slightly the application of this to regression, so I'm going to show it to you. And then we didn't do the derivation, but we did the absolute loss. So if you do the absolute loss, all right, this is a generalization, but if you do the absolute loss and you follow the little derivation here, it comes out that the Bayes estimator is the posterior median, right? 50% to the left, probability 50% to the right, okay? And if you use that, basically you have a generalization defined from the ratio of K2 over K1 plus K2. And when did you get the map again? The map estimate, what estimator we need? The delta function, okay? So basically, that is Y minus A to something that, that converges to 0. Okay? All right, so let me go back to the regression problem. So the notation here, and I think I am doing this crime even on the regression slides to come next week. I am using the notation from Bishop, so you may see this contradicting some other slides that I have in other topics that are related. So here X, think of this as the input. T, think of this as the true output of your model, all right? So what you want to do on the inference step, you want to compute the joint probability of X and T. And so your decision would be for every X to come up with some estimate of T, and that estimate is called the regression function, Y of X, all right? So at the given X, you want to say what is your approximation for T, and that we call it Y of X. So the loss function that we define is the squared loss function, and you notice is it is averaged with the joint distribution of X and T here, okay? This is what is called the generalization error, okay? And it's an L2 error. All right, and if you do calculus of variations, it comes up that the regression function is nothing else but the posterior mean. So here, I maybe need to be sort of a little bit careful, because in regression, when we call something the posterior mean is if you have data, X and Y, and you train things together, and then you compute the posterior mean. Here, really what I mean the posterior mean is the distribution of T for any given X is, that's what I call a posterior in this slide, right? To follow up with the previous slides. So the expectation of this distribution that you see here is basically the regression function. So I don't have any data yet when I am training the model, okay? So I wanted basically to clarify that here we are looking, we say the response at each point is some distribution. The average of that distribution gives me this function that I call it the regression function. So the regression function comes to be the expectation of T given X. Don't have any data yet here. And so here is how we're going to correct this to make it consistent with what we're going to learn next week on regression. So when I write the loss function and I average with respect to the joint distribution of X and T, I remind myself that this joint distribution of X and T, because this is a regression model, is coming with a lot of parameters theta that I have not said anything about. So for example, when you build a regression model, right, you say, I'm going to put a linear regression model that is X transpose times W. So that's my regression function. Or some basis functions of X transpose some regression coefficients W or theta. So I want to emphasize that there are parameters in this posterior here, in this joint distribution, and I call those parameters theta. So this, if you take this loss function and you minimize it with respect to Y of X, and you say, what is the best regression function, then you come with the posterior, you come with the mean of the distribution of T given X. But don't forget that that distribution of T given X depends on theta. All right, so what you need to do is, if you're going to do the full regression problem with a bunch of training data D, you're going to have to take this loss and then average it with respect to the posterior of the parameters of the model. And then if you do that, so if you take, you minimize this, it's going to give you the regression function, and then you're going to take a posterior of that with respect to the posterior of the parameters trained some data D, then, putting those two equations together, it tells you that the optimal solution, it is actually the true posterior mean, where I mean true, this is the response at X, which I call it T, but given the training data D. I am running a little bit ahead here in the context of regression, but I wanted to emphasize, right, what you will see in the literature as the optimal solution to this problem for regression, it says for every X, take the mean of this distribution of T given X. That's not the posterior of anything, all right? Because I have not used any training data. We haven't said anything on how we're going to compute this, okay? But we say there is a function that is really the mean response for the different X, the mean response for T for different X's, and that function is actually the one that minimizes this mean loss function, if you like. If you go and you put on the top of that the posterior of the parameters given some training data D, then that this estimator that you get from here, plug it in there, it actually gives you the posterior mean, which is an amazing result. So for example, and I'm running here, again, we haven't done any of this, but I want you will see this next week. If you have a simple regression linear model, and let's say your parameters are theta, so the mean function here, the regression function, is x transpose theta. Okay? So think that the response at every x is x transpose theta plus some Gaussian noise, okay? Which is defined by sigma squared. So effectively, when you minimize this loss function here, you know what this will give you? It will give you the regression function x transpose theta. So at any x response, the optimal response is x transpose theta. Now what you need to do is, you need to actually average with respect to the posterior of theta. But if your answer is x transpose theta, and you want to average over the posterior of theta, the actual optimal response then would be x transpose times the posterior mean of theta. And that result is universal, and it doesn't really matter on what details you're going to put in your regression model. It doesn't matter what prior you're going to have on theta, how you're going to do this or that. It's a universal result. All right, extremely powerful result that tells you effectively so you have your regression function, right? That's the one that minimizes that posterior expected loss that we saw it. And then when you average with the posterior of theta, what effectively you need to do is, instead of putting theta there, you're going to put the expected value of theta computed from all your training data. And this is, again, this is an amazing simple result that it's applied to regression in different contexts. Okay, let me see slide 22. So I remind you, for classification, it was very easy. Basically, we said you define, we discuss only generative models literally, at least up to now. So we start with the joint distributions of x in class 1 and joint distribution of x in class 2, and you get these different distributions. And effectively, we said the optimal classification boundary is the one for where, for example, the region that you declare to be class 1 is the region where the posterior of x given class 1 is higher than the posterior of x given class 2, okay? And, I'm sorry, the other way around, the posterior of C1 given x is greater than the posterior of C2 given x, okay? The way that you see, so if this is the optimal boundary, you notice to the left, everywhere here, the posterior of C1 given x is greater than the posterior of C2 given x. Okay, we introduced the concept of a loss matrix here. So not all decisions cost the same thing to you. So we gave this example with cancer. So if somebody has cancer, that's the true label, and your classifier says, you know what, you're normal, obviously the cost of that decision is significant versus somebody who is normal and is being declared that has cancer, unless they start doing therapy on you, right? And they radiate you for 10 years, and then they say, sorry. Okay, so when you plug in these things to the expected loss, it comes out basically that the different regions Rj that you will assign to class J are basically those regions that minimize this, this term here, okay? This is the summation of all overall classes of the loss matrix Kj, P of x sigma k. So effectively here, x comes from class Ck, but you assign it with some loss Lkj to class J, okay? So you need to select these regions so that this loss is minimized. And we did one example where we selected basically to check that this it's correct. If you take this to be 1 minus delta Kj, it comes out basically that the results are identical to what we discussed before, that the region J is the one that will give you the maximum posterior probability of Cj given x. I think this is where we were trying to discuss the last minute on the lecture. I even forgot what the date was with, it was this week or last week. We had so many cancellations. So this is what's called the reject option. So you're making decisions basically to what class to assign things based on the posteriors. But imagine if you have a multi-class problem, and let's say the maximum, the posterior that you can get is 0.5. Maybe 0.5 is not acceptable to you. You say, I don't trust this anymore, okay? So what you do is in these methods, you select a reject option, and you say any posterior probability that is, when I have the maximum posterior probability to be less than theta, I am going to reject. So here it's not only you classify and misclassify, but also you reject. You say no decision is to be made. And the calculation actually, it's very simple in the context, so you remember when we have a loss function, what we need to do is we need to define region Rj as the region that minimizes this loss, okay? So effectively we need to find, for all possible L's, the argument, the L, which I call here J, that minimizes this, average loss, if you like. So the options that we have here is to select J if the loss that we incur is below some amount, all right? So if the loss is not higher than some amount, I use J, the argument that minimizes this, and I'm going to assign to class J. Otherwise, we reject. So if you do this formalism, you can show actually for the very simple case that the loss matrix is 1 minus a delta function there, you can show that what I have here is the same as actually rejecting at the level 1 minus lambda. Okay? So it comes out that basically having a loss, basically accepting things with some maximum loss, it actually defines for you a reject criterion, in this case as simply as theta equal 1 minus lambda. When you build your classifiers for this accept reject cases, be sure you do your homework, right? So here's a classifier where the true label is J, and we assign it, let's say, to some class alpha A. So if the two labels coincide, we give loss 0. There is a possibility there that we may reject. We call that possibility C plus 1. C is the total number of classes. And there is a possibility that we will misclassify, and the loss for misclassification is lambda s. So the question is, what are the criteria? When do we select a misclassification? When do we reject? Okay? So let's do the following thing. You remember we accept, when we basically accept when we compute them, when the label we assign comes according to the maximum posterior distribution that we see here. So if you take this posterior for a given x, and so this is the probability basically that you will accept J max and assign it to the right, to the right class. It doesn't mean that J basically, if the true label is y equal to J, that you will actually recognize that. So there is a probability there that you will do some error, and that error is 1 minus this probability. Okay? And the loss in that case will be basically the misclassification loss times this error. And the only way you will accept this is if this loss is less than the reject option. So basically, you have to compare the error that you get when you misclassify versus the error that you get when you reject. So actually, in this case, you will actually accept something according to the standard criterion only if it is greater or equal to 1 minus lambda reject divided by lambda misclassify. Okay? So when you set basically those values, they cannot be arbitrary, right? So you need to come up with this sort of criteria that give you a sense on, of when the loss is less, because this is how you make decisions. There was a little thing that I wanted to tell you that we don't really have time. It's 12:20, so let me go rapidly. If you collect data, you try to classify things, right? But you can classify things using blood tests, using X-ray images. The question is, do you build an independent classifier for what classes you will use using blood tests or X-ray images? Well, the answer is you can actually build the posteriors for each cases, for each test, these data cases separately, but then once you're done, you can fuse the information together to come up with a better classifier. And the key ingredient to do this is, for a given label of the class sigma k, you can use a naive Bayes classifier, okay? So effectively, the data that you collect from different tests, given the labels, you can assume them to be independent. So if you do that assumption, effectively this equation at the middle, it tells you you can use results from multiple tests to do classification. And so each of these terms is built independently for each classifier, but you combine the two things together before you make decisions. And again, the whole idea is this is a simple application of sort of the naive Bayes assumption, where the futures xi and xb are independent given the labels for the classes. All right. There was a lot of there, right? I think we were done with this topic, and next Tuesday and Thursday we will